Welcome, and thank you for standing by. At this time, all participants are in a listen-only mode until the question and answer session of today's conference. At that time, you may press star one, unmute your phone, and record your name to ask a question. I would like to inform all parties that today's conference is being recorded. If you have any objections, you may disconnect at this time. I would now like to turn the conference over to your host, Mr. Jacob Richmond. Thank you. You may begin.
Good afternoon, everyone, and thank you for dialing in. I'm Jake Richmond. I'm the Senior Communications Manager for Earth Science at NASA's Goddard Space Flight Center here in Greenbelt, Maryland. And today we're here, as you know, to talk about NASA's PACE mission, the next big Earth Science mission that we are sending up. It is currently scheduled to launch no earlier than February 6th, and it is the Plankton Aerosol Cloud Ocean Ecosystem mission. And I'll just take a minute here to kind of introduce this mission that has become very close to my heart. As a communications person, this tends to happen, but it is a truly exciting mission, and I'll tell you why. I mean, basically what we're talking about is water and air. So two elements that are fundamental to life itself. And as someone who works in earth science on the communication side all the time, we think of Earth as, you know, we often hear it referred to as the third rock from the sun. It's a planet. It's the big hunk of rock floating around the sun. And, you know, maybe that's because we are all just land dwellers. We are stepping from one piece of solid ground to the other every day. But in our bones, we know that our home planet is much more than that. And at NASA, we think of it as much more than that. We often say, you've probably heard us say, Earth is a system of systems. And while we do study the land quite a bit, we study all those systems and how they influence each other, because they do influence each other. So although land is where we spend our lives as humans, we also know that just in terms of space and quantity and mass, Earth's land is dwarfed by its oceans and by its atmospheres. So it's no surprise then that when you listen to people who are on the PACE science team talk about the ocean and its atmospheres, that we've come to believe and feel like basically a lot of our earth science mysteries that are still out there reside in those two domains, in the water and in the air. And PACE is here to help solve some of those. A lot of them are invisible to the naked eye. Even you need a microscope to check out the kind of things that we're going to be studying. We're going to be sending instrumentation up to space to look at these things that are fairly invisible to us. And we're looking forward to all of you here helping us tell that story about what we learn. Before we officially get started, I'll just say, to indicate you have a question, please press star one. And then please ask one question at a time. We should have time for follow-ups, but if you do have a follow-up to your first question, just go ahead and queue up again, press star one again after your question's answered, and we will get to you. So, that said, with us today, I'll give you our participants from the NASA side and one other special guest. So with us today, NASA Deputy Administrator Pam Melroy, NASA Earth Science Division Director Karen St. Germain, PACE's Project Scientist Jeremy Werdell, and also PACE's Project Manager Mark Boyton, PACE's Deputy Mission Systems Engineer Noosha Haghani, Netherlands Institute for Space Research Atmospheric Scientist Otto Hasekamp. They're here because SRON, as that institute is known over on our side of the Atlantic, they helped develop one of the instruments that's going up on PACE, and Otto will tell you all about that. And then finally, we've got NASA's Water Resources Program Manager and, up until recently, the lead for PACE applications, and that's Erin Urquhart. So I'll let them all introduce themselves briefly before we get to the questions, and I'll just remind you again now and maybe one more time, when you can raise your hand at any point by pressing star one. So with that said, Pam, over to you.
Good afternoon. I'm Deputy Administrator Pam Melroy, and I want to thank all of you for being here today, because we're finding ourselves at a really critical juncture where shifts in the global Earth system, including climate change, are accelerating, and the impacts are growing in both frequency and intensity. Just last week, NASA announced that once again, the average surface temperature on Earth last year reached record highs. This data serves as a confirmation of what billions of people worldwide have experienced over the last year. We are undeniably in the midst of a climate crisis. Our planet is undergoing transformative changes, from the surge in extreme weather events and devastating wildfires to the rising sea levels. NASA is not just a space and aeronautics agency. We are a climate agency. We leverage the unique vantage point of space to study our home as a holistic planet, collecting vital Earth science data. This information is then available to people worldwide, empowering them to make informed decisions on how to safeguard our planet and its inhabitants for generations to come. So no wonder I'm very excited about the upcoming launch of PACE, Plankton, Aerosol, Cloud, Ocean Ecosystem Mission. PACE holds the promise of deepening our understanding of how microscopic oceanic and atmospheric particles impact our climate and our livelihood. It will deliver first-of-a-kind views of the phytoplankton that convert carbon dioxide into cellular material to feed oceanic life. This microscopic aquatic universe provides the backbone of our critical fisheries and plays a major role in drawing carbon dioxide out of our atmosphere. But it can also introduce harmful algal blooms that sometimes close beaches and shell fisheries and contaminate drinking water. Additionally, PACE aims to unveil the intricate mechanisms by which aerosols and clouds influence the absorption and scattering of the sun's energy by Earth. Aerosols, as they circulate through the ocean and atmosphere, play a pivotal role in cloud formation, thus influencing the behavior of weather systems. And unraveling this very complex interplay could provide us with the invaluable insights into the occurrence of extreme weather events. Moreover, such knowledge could guide policy decisions geared towards mitigating their effects and ultimately enhancing our ability to prepare for and respond to those events. So in essence, PACE represents a crucial step forward in our ongoing commitment to unraveling the mysteries of Earth's climate. Through missions like these, NASA continues to lead the way in advancing our understanding of the climate crisis and equipping us with the critical knowledge needed to address its challenges effectively. Thank you, and back to you, Jake.
Thank you, Pam. Next up, we've got the Earth Science Division Director for NASA, and that's Karen St. Germain. Over to you, Karen.
Great, thank you. It's terrific to be here with you all. I'm going to talk to you a little bit about how PACE fits into the broader Earth science portfolio. So today we have more than 24 NASA Earth science missions orbiting our planet, studying our oceans, our land, our ice, and our atmosphere. These Earth observations tell us how change in one part of the Earth system is driving and is driven by changes in other parts. Variability that we see as changes in our weather patterns, our ecosystems, and our climate. We're able to collect these measurements on a global scale because of our vantage point in space. And PACE is a great example of NASA's ability to develop innovative technology, put it in orbit, develop an advanced scientific research, build models from that understanding, and then deliver applications that are useful to society. From orbit, PACE instruments are going to measure the distribution and type of tiny plants and algae called phytoplankton, and also observe clouds and airborne particles called aerosols that both absorb and reflect sunlight. And this information is going to greatly advance and add to our understanding of ocean biology and the relationship between ocean life and our atmosphere. Integrating PACE science and data with research and information on the ocean's physical science that we're getting from SWOT, which we launched a little more than a year ago, we're going to enter into an entirely new era of ocean science. And when we combine PACE with data from SWOT and other missions in our fleet, we will learn more about, for example, how El Nino and water temperature impact biological productivity, how currents and eddies and the impact of sea level rise are changing ocean life, how carbon dioxide gas is exchanged between the ocean and atmosphere, how the role of ocean biology in cloud formation, and conversely, how aerosols fuel ocean biology. These all come from the combination of these missions. I've long said that our new Earth missions like PACE do for our understanding of Earth what the Webb telescope is doing for our understanding of the cosmos. We also consider PACE one of our Pathfinder missions for our next generation Earth System Observatory because applications and user communities were identified at the onset of mission development. It's also built with international partnerships, and open data and science will be done according to open science principles from the very beginning. Thanks very much. Back to you, Jake.
Thank you, Karen. Next up, we have the project scientist, Jeremy Werdell. Go ahead, Jeremy.
Thanks, Jake. Hello, everybody. Thank you so much for joining this call. I am the project scientist for this mission, which basically means that I have day-to-day responsibility for the overall scientific direction. I hope my enthusiasm becomes contagious for all of you. Our scientific community has been thinking about this mission for over 20 years. I've been involved since its realization as a real NASA mission for the past 9.5 years, and now we sit 20 days from launch. So there is a combination of anxiety and pure joy bubbling through me here. Overall, as you've heard from Pam and Karen, this is NASA's next great investment in the combined study of our home planet, sea, and sky. And really, we do this by looking at invisible things from space. Science basically boils down to is a monitoring of reflected sunlight. We do this with 3 instruments on the observatory, and while they were all built to do certain things exceptionally well, they complement each other beautifully and have cross-purpose in different disciplines. The primary instrument has the acronym OCI. It was built at NASA Goddard, where I reside. And then there are 2 contributed instruments that are multi-angle polarimeters that do really interesting things about how they see the invisible universe in very, very unique ways. And one is a contribution from the University of Maryland, Baltimore County, and the other from a consortium of organizations in the Netherlands. And of course, none of this would be possible without the amazing team we've integrated with at Goddard, who you'll hear from. But wrapping this up, this is a true mission of discovery. In my 20 years, it's the first one scientifically I deeply feel that I can grow into. And I think I speak for the community when I say that. I'm an oceanographer by training, so my interest, of course, is the aquatic universe that we can't see with our naked eyes. Phytoplankton, algae, the base of the food chain. Some are trying to get you, but most of them don't want to close beaches. They feed fisheries and support our economy. You'll hear from Otto about the atmospheric applications that we're capable of, but at its heart, this is a mission that spans multiple timescales. We're studying and revealing new things related to our climate, but we're also providing a ton of new information about things we care about in our day-to-day lives. So getting back to phytoplankton, sure, there are harmful algal blooms that people care about. There's a lot of recreational and economic and societal benefit to those measurements. But yes, we're also looking at the global ocean, understanding where all of the carbon is going and how phytoplankton play a role in feeding fisheries in our changing ecosystem. So I could talk about this endlessly, but others have a role here. So I will turn this back to you, Jake. But thank you again, everybody.
Thank you, Jeremy. Next up, we've got the PACE project manager, Mark Voitin. Go ahead, Mark.
Hey, thanks, Jake. Good afternoon, everyone. Let's see, Jake, Pam, Karen, Jeremy. I have to tell you, even though we're on the phone, your enthusiasm for PACE is coming across loud and clear here at Astrotech, where we're processing the observatory, the PACE Observatory, for its imminent launch. So my job as the PM really is just to manage the cost, schedule, and performance of the observatory, and it is an extremely exciting time readying the observatory here at Astrotech for its imminent launch and getting it commissioned and then in an operational state. So all that's right ahead of us in the months ahead. And what's also exciting is being a part of the everyday person who will benefit from all of the data that PACE provides. We'll launch it, and then we'll operate it, and all of us every day will benefit from the data that PACE provides to us on a daily basis. So that's all I have. Back to you, Jake.
Thank you, Mark. Next, we've got the Deputy Mission Systems Engineer for PACE, and that's Noosha Haghani. Go ahead, Noosha.
Thank you, Jake. Good afternoon, everyone. My name is Noosha Haghani, and I'm the PACE Deputy Mission Systems Engineer. I'm also here at Goddard Space Flight Center, although currently I'm at ASO, the Astrotech, doing the payload processing facility for our last few days before launch. My role has many aspects to it. Mission systems engineers are responsible for most of the technical decision-making involved with design and development of the observatory. Systems engineering generally first starts with designing and architecting the mission on paper. We then work with a series of discipline engineers in specific subsystems like command and data handling, attitude control, electronics, guidance, and navigation to build, test, integrate the observatory, including all its instruments and subsystems. So that's always a very exciting time for us. We try to ensure that all the final product that we deliver meets all of Jeremy's science requirements that he has. So there's a constant negotiation with the science group and with project management about what can we do with the capabilities that we have and the current technology and the budget that we have. It's very exciting. We have a variety of engineering disciplines that we're responsible for. That includes electrical, mechanical, propulsion, guidance and navigation, contamination, thermal. I'm just naming a few of them. That's not all of them by far. It's been very exciting for me. I've been on PACE since 2014, so it's a long road. I'm very happy to be here. Thanks for having me, Jake.
We appreciate you being here, Noosha. Next up, we've got the Senior Scientist with Atmospheric Specialty from the Netherlands Institute for Space Research. And again, that's Otto Hasekamp. So go ahead, Otto. Introduce yourself, please.
Thanks, Jake, and good afternoon, everyone. So I'm Otto Hasekamp. I'm an atmospheric scientist at SRON, the Netherlands Institute for Space Research. I'm the principal investigator of SPEXOne, which is one of the 3 instruments on PACE, as Jeremy mentioned already. So this SPEXOne instrument, it was developed and built in the Netherlands under the lead of SRON as a contributed payload to the PACE mission. And what SPEXOne will measure is atmospheric aerosols, and these are small particles in the air. And these aerosols are air pollutants, but they also have an important effect on climate because they cool the Earth and mask the warming by greenhouse gases. But we really don't know by how much. And the reason that these aerosols cool the Earth is that they reflect back sunlight back to space. And in this way, they cause a dimming of the solar light. And this means less energy is available to warm the Earth. Another reason why aerosols cool the Earth is that cloud droplets form on aerosol particles. And more aerosols means there will be more cloud droplets. And that means, again, that the clouds will be brighter, also cooling the Earth. And with the measurements of SPEXOne, in combination with the other instruments on PACE, I expect we can do better climate predictions. That's it. Back to you, Jake. Thanks.
Thank you, Otto. We also had, until a few moments ago, Erin Urquhart on the line, and she just let me know her call got dropped. So I think she'll try to dial back in. But just so you all are aware, on the media side, Erin has been leading the science applications part of the PACE mission for a long time, and she just took on a new role at NASA headquarters this month. And so now she's the program manager for water resources at NASA. So it's a big step up, well deserved, but she's also got a lot of institutional history and knowledge about how PACE is going to be applied in society. So if you have those kinds of questions, I'll let you guys know when she's back, or maybe Vanessa, our operator, can do that. So, but for now, that was her intro, and we will go ahead and get started. I'll just remind you all, if you have a question on your phone, press *1, and our operator will get you guys all in line, and she will indicate who is up next.
Thank you. We will now begin the question and answer session. If you would like to ask a question, please press *1, unmute your phone, and record your name. Your name is required to ask a question. If you need to withdraw your question, press *2. Again, to ask a question, please press *1. Jeff of Space News,
Vanessa.
your line is open.
Hi, good afternoon. This is Jeff Faust of Space News. Two quick questions. One, how long after the launch will PACE start returning science data? In other words, how long is the commissioning period for the instruments? And then two, do you have a overall cost for PACE that you can provide? Thanks.
All right, let's take these one at a time, like I was asking at the beginning. Thank you, Jeff. So that first one, Jeremy, the question about when it'll start delivering data, I'll kick that one over to you.
Got it. Thanks for the question, Jeff. So we have officially a 60-day on-orbit commissioning period. Roughly in the middle of that, the instruments will begin data collection. There will be a short period of time where we evaluate the quality of the retrievals, but the expectation is around somewhere between day 40 and day 50, we will release our first light to the public. And after that moment, we will start distributing data. So I should note that there is no period of exclusivity on the data stream. It will be available to the international public along with data visualization tools and source code. So we're hoping that the community dives in super fast and the discovery begins. Back to you, Jake.
All right. We'll get you your second answer here right now, Jeff. Just for everyone, if you could just limit your question to one at a time to make it a little easier on us handling the administration of this, that'd be great. But no issue here. So Mark, his second question, I think, was the budget allocation for PACE.
Oh, yeah, thanks, Jake. Okay. Hey, Jeff, so I have an agreement with NASA headquarters. So my budget for the full life cycle cost is $939.3 million, and that's what we're operating within.
Yeah, Jake, this is Karen St. Germain. I probably ought to jump in here and just say that at the top line, including headquarters reserves, the total budget for the mission is $64 million.
You broke up one little bit right as you were saying the number. Karen, can you repeat that real quick?
Yep, sure. Including headquarters reserves, the total top line is $964 million.
Great. Thank you. All right. Vanessa, who do we have next?
Thank you. Let's see. Will Robinson Smith of Space Flight Now, your line is open.
Yes, hi, Will Robinson Smith, Spaceflight Now. Thank you so much for taking the time to talk with us today. Question, I suppose, for Jeremy Werdell or another member, if it's best suited for someone else. Assuming things go, as optimally as expected with launch, what is the expected or best case scenario mission lifetime for the PACE spacecraft if the Falcon 9 is able to, put it where it needs to go as ideally as possible? What are sort of the upper limits of how long this thing can last? Thanks.
Go ahead, Jeremy.
Okay. Thanks for the question, Will. So the answer that I liked to give for this one when I'm in a mission review is that the scientific community expects 25 to 30 years out of this mission. But that, of course, is a little bit in jest. The defined mission life cycle is 3 years. We have propellant for 10 or more years. We've already had negotiations with headquarters about extended mission life, and there has been, of course, testing for at least double the 3 years. And then if we think of the pedigree of other instruments and observatories built at Goddard, such as MODIS, and I'm sorry for the acronym SOUP, they have entered their third decade. So the range is going to be from 3 years to at least a decade, in my opinion, of all of this, which is really great because as a climate mission, that long time scale is very important. Back to you, Jake, or if anybody else wishes to chime in on that.
Thank you, Jeremy. All right. Vanessa, who's up next?
Thank you. Ryan Riznick of Vox, your line is open.
Hey, I'm interested in the climate science aspect of it. You're talking about aerosols and studying them. And I know this is currently a bit of a debate in the climate science space of how much will aerosols play in cooling the Earth and, how much of global warming is going to accelerate due to us not completely understanding the role of aerosols. I'm interested, is this mission likely to solve this debate? I believe I heard that we might do better, but I'm curious if this is kind of the missing data that atmospheric scientists are looking for. How far do you think this will go to give us a better picture of the climate future?
That is a great question for you, Otto. So go ahead.
Yes, thanks for this question. So as I briefly mentioned in the intro, so PACE will deliver a lot of data that will help us to quantify better the aerosol effect on climate. So right now it's the largest uncertainty in quantifying the energy balance of the Earth. I think in degrees Celsius, the error bar is about 1 degree cooling. So our best estimate is half a degree, and it can be anywhere between 0 and 1 degree or even beyond. PACE will provide very important measurements. We need these measurements in combination with model development and in synergy with other satellites, like, for example, EarthCare, to really tackle this problem. But a lot is going to happen. So we have the EarthCare satellite from ESA. There's a lot of model development going on. And we have PACE coming up with very important measurements. So my expectation is that all these things together should reduce the error bar on the aerosol effect on the energy balance by a factor 2.
Thanks, Otto. I think Karen had something to add to that question as well. So go ahead, Karen.
Yeah, that was a great answer, and I'll just augment that a little bit by talking again about the relationships between the PACE data and the data we get from other missions. For example, right now we are building we're developing the missions for the Atmosphere Observing System. The key element here is that the relationship between aerosols in the atmosphere, those are small particles or liquid droplets, the relationship between those aerosols and the clouds that form around them, those aerosols act as seeds for the clouds, the exact makeup, size, so composition, size, shape, and where they are in the atmosphere have a huge impact on the kinds of clouds that form, whether they are bright, highly reflective clouds with lots of tiny, tiny droplets, or heavier, darker clouds that absorb the sun's energy. So it's really by going, we can go after questions like that, that question is the biggest source of natural uncertainty in predicting climate change. So it's in a combination of PACE and these atmospheric missions that will really be able to get after some of those very challenging questions about the feedbacks in the Earth's climate.
Appreciate that very much, Karen. And I'll just, since I'm not one of the experts for you to quote, but since Brian asked, I'm a former weather forecaster, and I'll just mention one of the questions that that's come up both with regard to PACE and with the down the road missions NASA's planning like AOS. But the question of why do clouds form where they form? Why do clouds have, why does that cloud stop there versus the open sky next to it? Those are aerosol questions, and as a weather forecaster, they taught us back in those days that we need cloud condensation nuclei to just get a cloud in the first place. So that's one of the reasons why I'm fascinated by what PACE is going to learn about aerosols, because it's just interesting to think about how we know very little so far about why a cloud forms, exactly where it forms, and why it doesn't. So welcoming more questions about that for sure. And while I have you, I'm going to mention that Erin Urquhart was able to dial back in. So again, she's here to talk about some applications if you have those questions. Erin, if you wouldn't mind, I'll give you your chance now to introduce yourself officially real quick.
Yeah, thank you, Jake. Good afternoon. Apologies for my technical difficulties. You would think as someone who's involved in the launch of a global Earth observing mission, I could figure out a landline. But to prime your PACE societal benefit questions, I just wanted to take a second and talk about applications. So in addition to advancing science and research, PACE data will also be used to support practical applications that will benefit society. The goal of the PACE applications program is to really foster new partnerships and out-of-the-box thinking that will generate inventive solutions to support people like you and me. Data products produced by PACE will help us monitor water resources, things like recreational water quality, fisheries and harmful algal blooms, as well as air quality, and it'll help us respond and mitigate risk of natural disasters, including flood, volcanic, and wildfire events. A key activity of the PACE applications program is engaging individuals and groups to use PACE data for applied Earth solutions. We work with a global community of practice made up of scientists, academics, public health practitioners, industry professionals to apply PACE data to meet practical societal needs. The PACE applications program also aims to build awareness of the PACE mission and its potential benefits. Overall, our pre-launch PACE applications efforts will enable quick integration of PACE data into decision-making processes and operational tools after the launch event next month. PACE data will be publicly available, offering new ways to view the Earth and its ecosystems. Connecting PACE with applied science is key to realizing the full potential of this innovative Earth-observing satellite. And whether or not Jake mentioned it earlier, I'm the new program manager of the NASA Water Resources Program, and my research and applications expertise is water quality. So as you can imagine, I could not be more excited to kick off my tenure at NASA headquarters with a mission like PACE. Thank you for having me. Back to you, Jake.
Thank you for popping back in, Erin. All right, and I know we have a couple questions lined up again. So Vanessa, back over to you, whoever's up next.
Thank you. Megan of Scientific American, your line is open.
Hi there. Can you hear me?
We can.
Wonderful. Thanks so much. Megan Bartels of Scientific American. I wanted to dig into that Plankton piece a little bit more. Could you talk more about sort of what PACE will be able to see in that front, why that information is important, and then does that fit into the climate aspect of this as well, or is that strictly on the water quality side? Thanks so much.
Everyone get comfortable. Jeremy Werdell is about to talk about phytoplankton and plankton, and there were no clear borders on where he has to stop. So go ahead, Jeremy. Can't wait.
Oh, yeah. Buckle up, everybody. That's a great question, Megan. Thank you. I can talk about phytoplankton endlessly. So the way we measure them from space is effectively to look at colors of the rainbow. So we measure reflected sunlight, and right now, think of what we have on orbit as a box of crayons with only 8 crayons in it. And the colors that we measure are very intelligently placed so that we can separate a phytoplankton signal from other things in the water column, like dissolved material. Think of tea that might run into an estuary and make it brown, seawater itself, and so forth. And what we can do with that is pretty much nail down the abundance of phytoplankton. We can tell you how much of it is there. What we're not good at yet is telling you what community is there. And every community plays some different role in the ecosystem. It forms different kinds of base of the food chain. They sink at different rates. They have different nutritional values. They fix carbon in different ways. So with PACE, we are getting a box of crayons with 200 different colors in it. And the reason that we can get to communities from that is that all of these phytoplankton, just like land plants, convert carbon dioxide into cellular material from photosynthesis. And their photosynthetic pigments, which are the cellular structures that collect light, each community places them slightly different to be competitive. And by looking at all of the color, then we can see those different pigment placements, and that can give us clues and then some definitive answers about what community is there. And getting to climate, this is important because we know with our warming atmosphere that the ocean is also changing, and the community structures of phytoplankton are changing. So fisheries are fed differently. Carbon dioxide is being removed from the atmosphere at different rates and in different places. The interaction with the atmosphere, whether phytoplankton release gas to create aerosols that create cloud condensation nuclei, that's evolving. So there are a lot of players here because we as climate scientists want to know where the carbon is going, how it's being used, if it's being permanently removed from the atmosphere, maybe by something that sinks quickly before it can be recycled. All of this is really important. And right now we're somewhat blind to it from space. And where PACE comes in, of course, is just to answer those questions on daily global scales. So it has a lot of societal benefits in terms of the ability to do this. If you're thinking about harmful algae and fisheries, but it really does address some difficult climate questions, both in terms of distribution of all of these communities, how they're changing in time and space, but then their role in interacting with the atmosphere and vice versa, so that we can start being a little bit more interdisciplinary in our thinking. So that's a lot of words, but I hope it touched on what you were looking for.
All right, so
You're on Teams.
Oh, I'm sorry. I unmuted myself in the wrong system. Real quick, I was just clarifying that that when Jeremy was talking about communities, he meant phytoplankton communities. So with regard to societal benefits and applications and fisheries and ecosystems, PACE will be able to help figure a lot of that out and help actual human communities and coastal communities. But what is in that answer, he was speaking of phytoplankton communities. And I'll just quickly add, for all of you on the call, if you're looking to flesh out your stories about the role phytoplankton plays in our Earth system, the scientific facts about phytoplankton are wild and really fun. I know this because I've had to listen to Jeremy and sure. Otto, would you like to take that one?
I guess
Otto, you might still be muted, but there you go.
I guess this one is better for Jeremy, right?
Yeah, it could be either or.
I will defer to the atmospheric scientist, if okay.
All right, well, let's get an answer from both of you then. So, Otto, you go first, and I'll just let everyone know when it comes to weather forecasting, operational weather forecasting, the nitty-gritty of hurricanes. I'll just sort of as a disclaimer, that is the role of NOAA. They do that, and so a role that we play at NASA, one of the many roles we play at NASA, is to gather data about the atmosphere, particularly when it comes to weather, right? And that data over time helps to inform the models that NOAA ends up using and refining and improving over time so that NOAA's weather forecasts are better. So that's one way to answer it for like a layperson. But in terms of like, so Otto, maybe you can answer just in terms of how aerosols themselves play a role in convective storm clouds and how that can lay
oh yes, definitely.
science on top of more science.
So PACE and SPEXOne, they will provide measurements of aerosols and clouds. Aerosols will impact these clouds, will impact also how long the clouds live, but also how intense the precipitation is that comes out of the clouds. So how this effect is very uncertain, but once we have quantified it from a scientific perspective, from analyzing the different data, so the cloud data from PACE, from the HARP2 polarimeter, from OCI, the aerosol measurements, from SPEXOne, we can study the relationship. Once that is established, it can be implemented in meteorological models that are used for weather predictions. It's a bit on the longer turn. So first the science, then the operational application, but I see definitely perspective there.
Thank you. Yeah. Jeremy, did you have anything to add?
Sure. I'm going to come at it from more of a post-hurricane effect angle. One of the things that I believe is really interesting about the interdisciplinary science that we'll accomplish with PACE, not just with the three instruments on the singular PACE observatory, but in combination with the other fleet of NASA Earth observing satellites, is how everything fits together and how the biology of the system responds to these short-term and long-term events. And I think one of the neat things that we'll continue to reveal with an observatory like PACE is perhaps not exactly mechanisms for the formation of hurricanes directly, for example, but what happens in the ocean in the aftermath. You have these big cloud storms that are reflecting sunlight, but then they are accompanied by high winds, and high winds mix the surface ocean, which changes the nutrient availability to different phytoplankton communities. And the biology will respond. There are very interesting things that can accompany that. So just mentioning this because it's one of the aspects of the interdisciplinary nature that I and others are very, very excited about. But back to you, Jake.
Thank you. All right. Vanessa, I think we have another question.
Yes. Hey, Emily of Fox Weather, your line is open.
Hey, thanks for taking my question. I think this could go for Erin because it's a direct application, but Karen also mentioned El Nino at the beginning of the call, so maybe for her as well. I'm interested in some more specifics on how PACE will help scientists monitoring impact the El Nino climate pattern. Do you guys think it will be operating in time for those observations? Any more El Nino facts would be great.
Okay, so PACE's relationship specifically to El Nino. Yeah, that wouldn't necessarily be in the water resources or applications realm for Erin. That's kind of a tough one. It's a little niche. I understand where you're going. Jeremy, any light bulbs on that one?
Sure, and this touches again on watching a biological response to a much bigger player in climate. In fact, one of the predecessors of the OCI instrument, which will fly on PACE, which is called CWIS,
was the first observation from space on the response of the phytoplankton algal communities to the transition between El Nino and La Nina. And you can see this in the abundances of phytoplankton that were retrieved from space. And since you're talking about, in this case, equatorial upwelling in the Pacific, it's such a huge vast of oceanic real estate, it's just not observable from aircraft or ships. And so PACE will continue to do things like that, where you see how the living aquatic universe responds to these large climate cycles. And we'll be able to continue to see changes in abundances, but the added value of the mission will also be that if the phytoplankton communities behind those abundances change as well too. So it is another tool in the toolbox for understanding the effect and the response of the La Nina, El Nino transitions.
And I think Karen had something to add as well. So go ahead, Karen.
Yeah, I just wanted to add, in my opening comments, I mentioned the SWAT mission, which we launched just over a year ago. SWAT is providing extremely high fidelity observations of sea surface height. Such high fidelity that we can actually see things like eddies and currents, and we have more detail on the changes in sea level that are associated with the local changes in sea level that are associated with El Nino. So the SWAT mission is really is where we're going to get that physical oceanography that's closely tied to the drivers of El Nino. And then the combination of SWAT and PACE is really where we can start to understand that relationship between El Nino and the biology of the oceans that are so important, for example, to predict the impact of El Nino on fisheries, and to look at the relationship between upwelling of the deep ocean water that has the nutrients that allows fisheries to thrive and so forth. So it's really that combination. Hopefully that helps.
Thank you, Karen. I don't see any other questions in the queue right now, but we do have about 10 minutes left, and so I don't get a lot of opportunity to. Oh, okay, one popped up. We'll get to that last one here in a second. I don't get a lot of opportunity to ask our deputy administrator questions very often, but some of you may not know, Pam Melroy is not only the deputy administrator for NASA, but also a former astronaut. And as someone who has an earth science teacher for a wife and a little bit of the history of how much of what we think about our Earth system and our respect for the scientific endeavor of Earth science comes from that famous photo from Apollo 8, which we know of as Earthrise. It's the picture of Earth kind of blanketed by black space from a camera circling the moon. And since Pam is the only person on this call who's seen the Earth from above our atmosphere, I'm just curious, Pam, if you could maybe give us a little bit of an idea with that vantage point in your mind's eye, and now as the DA for NASA and all this Earth and climate science, kind of at the forefront of what we do, how has that resonated with you and your position?
Thanks, Jake. Big trouble asking me a question like that. I could take up the next 10 minutes, but I won't. I do appreciate being asked. It's well known. I think that astronauts get such an extraordinary perception of the Earth that it really leads to a change and a shift in your viewpoint. And it's called the overview effect. And there's many different dimensions to it. Largely, I think it has to do with the fact that the Earth is one large connected system, that it is our home, and it is humanity's spacecraft, and the same attitude that a crew takes when their vehicle, their spacecraft, is having issues. It's critical that the team work together to get the data that you need to analyze the problem and then execute a solution. And so I think it's very much how both the administrator, who has also flown in space, and myself view our Earth science portfolio. And what I find notable about PACE in particular is that it's actually building on a generation of earlier Earth satellites to really home in on what the critical data that we're trying to get to resolve some of these crucial questions. And I know that's been covered extensively by the other much more knowledgeable members today, but I think that the importance of it and the perspective that the Earth is a huge integrated system and that we have to protect it as its crew members is really what it comes down to. Thanks for asking, Jake.
Thank you for answering, Pam. Thank you for answering, Pam, and I think Jeremy would like you to know that he might be able to be an even better project scientist if he's able to get up and into space and look at Earth as well. So just take that under consideration as you see fit.
Absolutely.
I think we have one more question at least. Vanessa?
Will Robinson Smith of Space Flight Now, your line is open.
Yes, hello. Thanks for taking a follow-up. Just a quick launch timing related question. On the release for this conference, it mentioned that the launch is no earlier than 1:30 a.m. on February 6th. I just wanted to check that that's still the plan, if that's an instantaneous launch window or if there's a longer window beyond that. And if you have the time with the second, it would be fabulous. Thank you.
Down to the second. All right, that one's for you, Mark. You know.
Yeah, thanks, Jake. Let's see. The plan is pretty much as you stated, instantaneous over a period of 90 seconds. We'll go for the center of that. But yeah, that can occur every subsequent day. So if we don't launch on the 6th, we will try again on the 7th, the same time, and so on. So that's all I have, Jake.
Thanks, Mark. Hopefully that got it. Vanessa, do we have any left?
We show no further questions in queue.
Okay. I have one more for Noosha. So, Deputy Mission Systems Engineer. I definitely wanted Noosha to be here to answer any of the engineering questions that may come up. We didn't have any come up, but I will just say this, Noosha, for those still on the line. What is something surprising about this long saga engineering project management that you've been dealing with PACE for so long? Give us something surprising that you've experienced in your role that maybe a regular person wouldn't think of.
Oh, Jake, that's a good question. So what I would like to say is most surprising for me is how humbling it is to work on this project. I myself am an engineer, and PACE is what we call an in-house project. So every day there's a new troubleshooting endeavor that we undertake. Every day there are complex problems to solve, and you'd be surprised how often that those occur. But what's great about it is we have a team here with a very detailed subject matter experts around us, and every day we are troubleshooting, solving problems, and getting one step closer to the finish line. That process is exciting. It's at times very stressful, but at times also very gratifying and humbling to get to the final product. And I can't say that I've not enjoyed it. I've loved every minute of it. Back to you, Jake.
Thanks, Noosha. I appreciate hearing that. I haven't been on, working on PACE in my role for nearly as long as you have, and I've already kind of gotten a sense of the same. One thing that's great about working at NASA, anywhere basically, is that so much of what we do at NASA does culminate, and it works up to this beautiful thing. Often at launch, then there's first light, and then there's everything that comes after. So And I think while you were talking, we did get one more question, so we have a few more minutes. Vanessa, if that's true, go ahead.
Thank you. Dinah of USA Today, your line is open.
Thank you. I did have another question. There was a reference earlier to the ability of PACE to help mitigate natural disasters, and I wondered if someone could just speak a little bit more about that.
Yeah, that's probably along the same lines as the hurricane question. Erin, I'll just ask you, in the portfolio of early adopters and applications, does that match up with anything that you're working on or working toward, natural disasters?
Yeah, thanks, Jake. That's a great question. So as Jake mentioned, we have something called the Early Adopters Program. And so these are a group of academic scientists that we've been working with for the past 4 years with simulated PACE data to get ready for launch. In terms of our existing early adopter profile, we don't have anybody per se that's working on mitigating risk of natural disasters. That being said, moving forward, using real PACE data, we are really looking forward to looking at post-disaster risk on things like water quality, air quality. And so when I say natural disasters, I'm thinking about things like hurricane, extreme weather events, flooding and drought and how that's going to impact kind of inland coastal water bodies. Also thinking about how are we going to understand and mitigate the risk of volcanic emissions on air quality and health. And then going forward, thinking about, we didn't touch much on kind of the terrestrial applications of PACE here, but combining PACE data with other Earth observation data, starting to look at how climate events and natural disasters are going to impact our terrestrial ecosystems and food security moving forward. So not exactly sure if that gets to your question specifically, but I hope it helps a little bit.
And I'll just add, we can certainly take that if you want to follow up with me via email to get a little bit deeper into that. We can. I think thing to keep in mind if you wanted to follow up just in terms of framing the question, it's because the Earth is a system of systems, right? Those natural disasters tend to be large disruptions to multiple systems at once, and so even if it's not something that's currently in the early adopters portfolio, chances are PACE and the data that it's delivering about atmospheres and even phytoplankton, which, that ocean ecosystems get disrupted by various natural disasters, PACE will play a role. One example that we've used is with a volcanic eruption in Australia, following that ash as it eventually goes in the atmosphere and then gets deposited down into the ocean. Because it's so rich in iron and nitrogen and different nutrients, that's where a phytoplankton bloom can happen that wouldn't have happened otherwise, right? So those interactions would be inside of what PACE can help us uncover, and it's usually going to be dynamically within the context of other measurements we have, right? Karen, did you want to add something to that too?
Yeah, I'll just add, I agree with Erin. A lot of what we're talking about here is really understanding the effects of natural disasters, including potential cascading effects. And I'll just I'll give you one example from a few years ago when there were the very, very large wildfires in Australia, 200 square kilometers, I think it was, burned, and shortly thereafter, thousands of kilometers away in the southern Pacific, we saw an algal bloom in a part of the ocean where that's not expected. And the reason it's not expected there is because there aren't nutrients at the surface of the ocean where phytoplankton grow. But the aerosols from the wildfires deposited nutrients there as they fell out of the atmosphere, and then we had the ingredients, nutrients plus sunlight, for phytoplankton to bloom. That was an unexpected result, and that was an enormous phytoplankton bloom. So there are lots of, as Erin and Jake mentioned, connected effects associated with any kind of large natural event.
Thank you, Karen. All right. We went a little over, which is great. I'll just add for those, for the reporters, so if you got the call-in number for this and you're on this call, in that same email, you should have everyone's name and title spelled correctly. But I'll add as well, please don't hesitate to get in touch with me if you'd like. If you have any other questions, if you want to schedule another interview, we are, just a little bit more than a couple weeks out from PACE launch. We are very keen and available to schedule something with anyone on this panel and plenty of other subject matter experts from many different disciplines around the PACE mission. So just reach out to me and we will get you set up one way or another. And thank you again to everyone who joined on the NASA side. Thank you again, Otto, for joining from SRON. And especially thank you to all of you in the media who decided to take part of your day today to learn more about PACE. We really appreciate you helping us tell the story. All right, I think that's it, Vanessa. And thank you as well for helping us run this.
Thank you. That concludes today's call. You may disconnect at this time. Host, please stand by for your post-conference.